So I also want to apologize for one more thing. I gave you some information last time that it turns out is not quite right. Specifically, I thought that basically once someone drops out of the class, the number will show, like there will be 119 people, and then anyone can go in and log in. Apparently, after the first week of classes, this is not true. Even if there are spots opened up, I have to give you a permission code. You can't just go in yourself. So I talked to a number of people, and I decided the only fair way to do this was to basically institute a wait list based on when people email me. And people have emailed me since May. So I have a wait list. It's not that long as you might think, because a lot of people basically either got into the class or gave up and did something else. So there is a wait list, and I encourage you to email me if you are in this class right now, but you're not able to actually register. I didn't want to post this on the forum because the only people who can access the forum are people already registered. So if you're in this class right now, you haven't been able to register, send me an email, preferably as soon as possible, preferably right now. And then and I will put you on the list. There's no guarantee even one person on the wait list will get it, but right now I think we have -1 slots available. It was -2 before, it's only -1 slots now, so that's good. We might actually have 0 slots at some point. So we'll see what happens. I won't really know till the drop deadline, of course. All right, so that's so much for administrivia. I will ask a question, except that I haven't given you anything to ask me questions about, so it doesn't seem very fair. So I won't ask for any questions on that. Let us start by reviewing what we did last time.
But it's painful to my ears.
Yeah. Is everything okay?
Yeah.
Okay.
Yeah, it's fine.
So let's review the stuff we did last time. I talked about recursion, right? And so the cornerstone concept of computer science, right? The idea that to solve a problem, you can reduce it to a smaller version of itself. And by doing this repeatedly, or many versions of itself, and by doing this repeatedly, you can solve a problem essentially without having to solve it, because the recursion theory takes care of the problem for you. And the most simple example of how recursion can be used to solve problems is the paradigm called divide and conquer, where you take a problem, you divide it into pieces, you solve each piece recursively, and then all you have to do is figure out how to merge them together. And some of that conquering, merging step is usually a lot easier. And so that gives you a benefit. We then talked about, well, how would you go about analyzing the behavior of such an algorithm? As I said, to analyze correctness is relatively easy. You have to the recursion can be proven correct by induction, essentially. That you rely on the fact that if you could solve a smaller version of the problem, then those things are correct, and that's the inductive hypothesis. And all you have to do is verify that the merging step is correct. So in a divide and conquer algorithm, the only part you actually have your hands on is the merge. Everything else just happens by itself. So that's so much for correctness. And then I said, well, if you want to analyze the runtime, the way you describe the runtime of a divide and conquer algorithm is, of course, also recursive. You have some function for the runtime. It's defined in terms of itself, but for smaller values of the size of the input. And so there's this generic theorem called the master theorem that allows you, in many cases, to solve such recurrence just by looking at by pattern matching. And the divide and conquer, the master theorem we looked at, is the following. By the way, there were 2 problems I think we'd seen the board last time. I solved one of them, and I hope so. Mainly, I got the lights. I figured out that in order to get the lights on, you have to actually put a switch on. Something that I never knew before. So the switch on and work. So hopefully people in the back can see a bit better. The other problem I have to solve is get some colored chalk, which I didn't bring this time. But hopefully that will also help. So people in the back, let me know if you're having. I can make sure I write it more clearly than I should do. The master theorem says what? If I have a reference of the form T of n is equal to divide the problem into A pieces, each of size n over b, solve them recursively, and then merge them. By the way, I'm kind of lying here a little bit. This recurrence could describe 2 different kinds of algorithms. One is divide it into A pieces of size n over b, solve them recursively, and merge. Or do a bunch of work to decide how to divide them into n pieces of size n over b, then do the recurrence, and then merge. And that could capture both of those things. So there's a pre-recursion, post-recursion thing also that gets wrapped up in that function. And then there are 3 cases to consider. If you remember, someone from this section, give me a case. You just cite only. Anyone, stick your hand up, tell me your name, and give me a case. Yes. Wait, Praful. Okay.
So A times f of n by b is greater than c times f of n, or c greater than equal to 1.
Yeah.
So,
And let me actually actually, so when I said this last time, I thought they were interchangeable, but let me change this ever so slightly. Let me put this here, and let me put that here. And then what happens?
So the T of n equals.
So again, before you tell me the answer, tell me what this means in English, because that's more important.
Yeah. So it means that the dividing step is much computationally complex as compared to the merging step.
Very good. And so the right hand should be dominated by the effort to divide.
Yeah.
That's when we are thinking about it. Okay? You have to figure out which one is which. The effort should be controlled by the dividing, and so the answer is
Theta times
theta, not theta times,
sorry.
theta all.
n power log a base b.
Correct. Very good. Thank you. And again, the goal is not, please don't feel like you have to memorize these things. You know, the goal is to get some, okay, this is worse than that. There should be something like looks like this. You can actually prove this whole thing yourself. It's kind of tedious. You can write on. You can actually explicitly write on this expression and prove it for yourself. So don't think that you need to memorize this in any sense. It's not really necessary. You just have to have some sense of, okay, these different cases, and if I go look at the right textbook, I'll figure out the right case. That's all you need to remember from here. I want to mention one point. I forgot to say this earlier. Some of you had spoken to one of the TAs about your concerns about not being familiar with O notation. Now, I know there are many people here, for example, who are not from computer science. And so for you, this notation is a little cryptic. It's theta, what's all this stuff going on. I would strongly encourage you to get in touch with the TAs and also talk to the folks running the study groups. That's Tony, Charlie, where's Charlie? Okay, and John is also helping with the study group. So please talk to them. Please talk to the TAs. This is not material I will teach. This is material that usually you cover in an undergrad algorithms class. So if you're not exposed to this because you didn't take a CS undergrad degree, I understand, but you do need to do some remedial work of your own to catch up. So it's a basic shorthand for dealing with asymptotic analysis of functions. And there's lots of material out there. If you email me, I'm happy to give you lots of material to read, but you have to do this on your own time. Okay? So make sure you do that. If you're, so anyone who feels like they're a bit rusty with their knowledge of O, theta, small o, omega, and all this stuff, there's places to go learn about this, do it. Because I will be assuming that all of this makes sense. When I say theta versus O, there's a meaning for it, and then you know what that means. If I say small o, there's a meaning, and you know what that means, and so on and so forth. Okay? All right. So this is the first case. Okay, someone from that side, stick your hand up and tell me what another case would be. Nothing. Yes, your name?
Vidhi.
Vidhi, yes.
A of Fn.
Well, how about this? Tell me in English first what you want to capture, the idea you want to capture.
I want to capture the case where dividing is easier than the merging step.
Okay, very good. Go ahead.
So A into F of n by b is less than C of Fn. C.
Yeah, and we'll do the same modification I did here. The change that I'm going to do, but it's the same thing that you say. C times F of n for C less than 1. Right? And in this case, what will the thing that controls right now be? It'll be the
Merging step.
and so the answer will be T of n.
Theta of F of n.
Very good. Thank you. There's of course a third case, right? The third case is when they balance each other out. Okay. And someone from the back 3 rows. Anyone, stick up your hand and tell me what you think. You thought hiding in the back would prevent me from answering. Anyone, stick. I don't know. Yes. Sorry, your name?
Sriram.
Sriram. Yes.
So, the third case is when both the cost of abbreviation and merging are the same. So, A of F of n by b is equal to C of F of n.
It's equal to F of n, I think is what we
Yeah. So, C greater than 1.
There's no C. You get used to a pattern. This is C, and this is like, no, there's no C. They're equal. They're exactly equal.
The T of n is equal to theta of F of n times log n to the base t.
Very good. So these are the 3 cases that the Morse theorem covers. There are things it does not cover. There are things that fall into this pattern that it does not cover. And we'll see some of them in a bit. But hopefully you all remember this. Okay. We're going to do a little activity. Get a piece of paper out and I'm going to write down some references. I'm going to give you 5 minutes. I want you to spend 5 minutes thinking about any of these references you like and playing with them. These are going to be references that should be straightforward applications of the master. Or not. We'll find out. Okay. So, number 1. Okay, 5 minutes. If you need a question or clarification, just raise your hand and I'll run over to you. Let me know if there are any questions.
Sorry?
If there are any questions from there, just let me know.
Yeah.
They can hear you.
Yeah.
So remember, in order to apply the Gaussian theorem, you've got to match the case, and you have to, as someone was mentioning, often the problem will be, okay, what is the right value of C to pick? It doesn't matter what you pick as long as it satisfies the conditions. That's a proof in some sense of the right time is what you means. So that's what you have to do. And it's usually very easy to see what an appropriate value of C would be, but that's what you have to do that. Otherwise you don't have a complete argument. Yes?
Do we need to know the start point of these programs?
Oh, very good point that I did not mention and no one asked me about. These are recursions, they have to have a base case. It's kind of silly for me to tell you to solve these things without a base case. So for now, let's assume that in all cases, whatever the function is, the value at 1 is 1. Or 0. Actually, it's a big 1, just make it simple. Okay? Or you can assume anything convenient you want. You can assume that the function value at some constant number or less is some constant. Okay, cool. But that's a very good point. Thank you for bringing that up. So I'll just say P of 1 is equal to 1, S of 1 is equal to 1, G of 1. Oh, you asked me to check the answer? I'm not checking it. Okay, 5 minutes up. Now what I want you to do is find the person next to you, de-randomize the left and right choices appropriately, and compare answers. If there is a discrepancy in your answers, that's where the fun starts. You got 2 minutes. Is there any disagreement? Any people ready to go to an arm wrestling competition and settle the answer here? It's a time-honored way of settling theorems. Go to arm wrestling. That's right, I got my muscles. No? Everyone agree? Okay, next question. Did anyone have any questions about this process? There were some very nice questions that came up while you were doing this, and I'm going to mention them right now. But were there any other questions? Is it more or less clear on how you go about doing these things? You have a question? Yes.
How do we get C?
How do you get C? That was a question that came up. How do you get C? Okay, good. That's one question. Any other questions? I'm going to answer them in a second. What other questions do we have? No? Okay, good. How do we get C? So this seems to be how many of you felt, okay, this is something that you would like to know, you're not quite sure about how this works? Very good, very good. I'm glad you said that. Okay. How do you find C? So let's take the first one. Okay, we'll take the 3D on right number 2. Yeah? That's right. Okay. P of n is equal to 3Tn over 2 plus theta n squared. Okay. I have sudden bursts of amnesia and I no longer know how to do references. Could someone help me? Anyone? Okay, wait, let's see. We did the back 3 rows. We did this side, we did this side. Okay, the front 3 rows. Yeah, you asked the question, you wait. Sorry. Anyone else in the front 3 rows? Like to venture oh, you all did this, so you know how to do it. So don't volunteer other people. Anyone would like to take a hack at this? In the first 3 rows. Anyone? Come on.
Sure.
Okay, go ahead.
So
Your name is?
Nick.
Nick, yes.
So for this A is 3.
A is 3. Follow along, and if there's any step you disagree with or are confused about, please let me know. A is 3.
B is 2.
B is 2.
And our F then is n squared.
F is n squared. Yeah. And also one more question that came up. Well, is theta n squared, what should I do? Really what you should be doing is put some constant here, some dummy constant. Just to make things cleaner. But you know, if you know what you're doing, like with most things, you can ignore that. But if you don't know what you're doing, or you don't know that you don't know what you're doing, anyway, you should do this. Yes.
I'm not
Carry,
following that
carry
step.
right.
Yes.
Okay, yes.
Wow, okay. I'm not following how you got the f of n.
Okay,
There.
so let's look at this, and let's go back and look at this.
Yeah.
The f of n is the part that's outside the recurrence. It's the stuff you're doing when you're not doing the recursive step.
But this is calling for f of n, you're giving it n squared here.
F of n is the n squared. F of n is some function of n. In this particular recurrence, what is that function of n? Oh, well, it's some constant times n squared. Does that make sense?
Not yet, but I'll think about it.
So, okay, no, I mean,
It's
is that,
notational, I just,
This is maybe kind of related to what I was thinking about too. So basically, when it's big theta of n squared, we can replace wherever we see an f of n, we can replace it with the constant times n squared.
Yes.
Because f of n is equal to a constant times n squared for all n bigger than some
Right.
n naught or something
Okay.
like that.
does that help? Does that,
Yes, it did.
okay. So we have f, which we're going to replace by, yeah, some constant times n squared. Carry on.
So now we just need to solve for both.
Okay, so let's do it. So let's write down the AF. And I have to say, at one level, I feel bad that I'm making this sound so mechanical, because it's such a beautiful thing. It's not as, but one of the beauties of the Moss theorem is that it does make the mysterious mechanical. And mechanical in this way is a good thing, that you can just automatically figure it out. But I would hate to think that, you think that this is how we do stuff. Just, it's not as mechanical as all that. But having said that, let's carry on. So, A times f net over b. So you put 3.
Yep, so it's 3 times k n squared over 4.
So you do, okay. So I'll just do it.
Oh, yeah, sorry.
It'll be n over 2 whole squared. Let me just do it even slower than that, so we see what's going on. Yeah, and then I compare it to
dn squared.
dn squared. Okay, so now let's look at this. This becomes 3d over 4n squared versus dn squared. Okay, which case do we think should apply here? The second case, right? So now, what would an appropriate value of c be in this case? We know that this is less than this. We can write this as, so we can say that 3d over 4n squared is less than or equal to dn squared times 3/4. Yes, I just rewrote it. But now this number 3 over 4 is a number that's less than 1. That's my c. And I'm done. I was able to produce the c required to get this to work. So it's actually not that complicated. You just have to sort of extract it from by the expression. Does that make sense? Does that make sense? John? John?
I'm working on it.
No, sorry.
It's processing.
It's processing. Good. I understand that. But if any of you had confusion about, okay, yeah, all seems low, how do you pick the C? This is how you do it. You just match and do. Yes. Yes.
but we
Wait. Don't. Wait. Abhishek.
You got my name right.
Thank you. Sorry, I shouldn't look so enthusiastic. Yeah.
But we assume that the work required for the merging step is much more than the partitioning step. So then we take this part only. But now when we look at this seems to be have more exact same work for each of the parts.
Why is it exact? Is 3/4 less?
It's kind of less than equal to. It's not like.
But it's less than 3/4 of it. It's not less than 8. It's less than 3/4 of it. It's like I'm less than half your height. If I were less than half your height, that's not just less than your height. It's less than half of your height. That's significantly less. And remember, this difference is blowing up at every single level. This is the thing with recursion. These small differences, at every level you're going to see it. So it just starts compounding. And that's why it just sweeps it all away. So we haven't finished yet. So I've done this, I've selected the case. So now I've got the pattern to match, I should declare the answer. And so in this case, the answer will be T of n is equal to theta n squared. Right? Okay, yes.
C is less than 1 or greater than 1 in the second case?
The inequalities have to match. Yeah. If you're going to be less, you've got to be a lot less. If you're going to be more, you've got to be a lot more. There's no hedging about this. Okay, so if this is going to be less, greater than that, it has to be a lot greater. If it's going to be less, it has to be a lot less. Okay? Because remember, we want a significant difference between the two effects. Don't worry about the actual inequality, because you'll never remember it that way. You want a significant difference between the divide and the merge to make a decision. If you don't have a significant difference, then you have either equality or you're stuck. Okay? Does this all make sense? No.
Probably, I think like for any C greater than 1, or I mean,
Yes. So in other words, yes, correct, very good. So what I should be saying here, I think what's possible last time was, so this is case 1. I should say there exists a C greater than 1 such that this is true. In this case, I should say there exists a C less than 1 such that this is true. I think that's what you're referring to. And some people have mentioned this last time as well, that does it be true for all C? No. You just have to find one. And I'm sorry to mention this earlier. You find, as long as you find one that satisfies this, you're good. In this case, I found my 3/4, I'm happy. I'm done. Because again, you just need to show that there's a significant gap, one way or the other. As long as you do that, the whole geometric series just explodes on you, and everything goes on. Yes.
So we are in the second case, we are taking C of less than 1.
Because you are showing that the divide step is significantly less than the.
Yes. So my doubt was whenever you multiply a number by a number less than 1, so it's like dividing.
It's even less. It's even less.
Yeah. So it just reduces it, right?
Even more so. Yes.
Is this why Fn is significantly larger? So
Yes.
no matter what we multiply.
Yes, that's right. That's exactly right. Yeah. Yes. And your name is? Sorry? Sorry, can't hear you. Navi. Okay. Ravi.
So what is the significant difference?
That inequality. Significant. So I'm using significant difference metaphorically, but the mathematical definition of significant differences is a constant. That one is less than the other by a constant. That's strictly away from one. That's the important thing, right? I'm not less than this. I'm 0.99 less than this, and that makes all the difference. It's like if you put your money in a bank. Even if the rate of interest compounding is 0.1%, 1.01%, it will still compound exponentially fast. It's a slow exponential, but it will still compound exponentially fast, as long as it's more than 1. And that's exactly what's happening here. It's the exact same mathematics, the mathematics of geometric expansion. Yeah.
So in this first case, we take D and we say that it could be 3/4, which means that C can be 3/4.
The value choosing C 3/4 satisfies this inequality. Yes, that's all we need.
And then that gets us to that particular case of the master theorem.
That's right. Yeah, as long as we can find that one. Good. Okay, very good. Yes. Wait. You had mentioned it. No, I forgot. I'm sorry. I have my 7-slot memory. It's gone. So.
My name is Anil. Actually, how do you choose the value for theta of n square as b n square?
It's D is a dummy variable. It doesn't matter. It cancels on both sides.
No, I'm asking you that theta of n square. It's a polynomial of degree 2x.
Yeah.
It would be of the form n square plus n plus some.
It could. Still theta n squared.
So how do you?
It's still theta n squared. If your polynomial is 10x squared plus 3x plus 5, it's 11x. It's less than equal to 11x squared. Good enough for me. That's why you have theta notation. This is why you should probably sort of remind yourself of what the value of theta. You can absorb all those lower order terms into a one higher order polynomial, because in the limit that's the only one that matters. In the limit as n goes to infinity, all the other terms drop away. They don't matter. Only the big term matters.
So basically estimating.
Yes. 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 This will be a theme of everything we do. We use asymptotic analysis because it clarifies what's really going on. If I had to do different cases for different kinds of functions, it would be a nightmare. But what we're saying is that the top order term is all that matters. Yeah. Yes.
Since the
Your name?
Shobit.
Yeah.
Since the left side and the right sides have the same polynomial, that is why we are not worrying about the n naught factor or where n is greater than n naught, this inequality.
I want to say yes, but I can't. There's something like preventing me from saying that you're exactly right. It is sort of. We're able to ignore the n naught also because all of this is happening asymptotically. It's happening like out there, in the limit where good things happen. And algorithms will like bring that. I mean, in some sense, it's not just because of the same polynomial. It helps.
Yeah.
But even if they're two different polynomials, for example, you come to some comparison, one of the n naughts for one is bigger than the other, right? Just choose that one and do everything beyond that one. So I mean, if you, for now, if you want to think of it that way, that's fine. But that's not. It's not as complicated as that. You don't have to have. You can ignore the n0 even if they were different, because you just choose the larger one. Okay. These are all well and good. You can apply the master theorem, yay, whoop-de-doo. And but what happens if you can't apply the master theorem? That's when the rubber hits the road. I'm going to give you 3 minutes. Yes. Turns out that it's a very beautiful theory that is right from the it allows you not just to get tell you it's right now it is 0.5 and you need a whole book of basically you look at this complex plane, you look at the whole complex plane, and that tells you way more. You should think of this as a tool. I mean, no matter what your cost solution is, the way you analyze it.
No mic here. We need to actually plug it into this one.
The cost per operation.
Why do you mean? No, I don't need that. It's just one right here. Because I don't want to talk to her.
So think of this as a little that applies once you have.
So it's not that one.
No. Okay. Anyone want to venture a guess for an answer? Before I'll take questions about this thing, but anyone want to venture a guess for an answer at this point? But when I say guess, I don't mean this came to me in a dream. I mean this came to me in a dream and here's a proof. Anyone? Anyone named not Nitin or John? Sure, but guess one.
Just guessing, we will just make t n power 1 by 2, then it will come as 1 by 4 and so on. So
Yes, that's a good way to start. Very good way to start. Yes.
And then we'll add.
You have to figure out what happens.
Expand and
start. That's a very good way to start it. Just expand it out. When you're in doubt, expand. Any other comments, questions? Were there some questions from the set? Yeah.
We are not sure whether one is greater or the 2 and t of 2 is greater. So can we apply master theorem?
You can't, because in the master theorem, E is be a constant. Yeah. You have to expand. Right. Yes. Yes.
If we go a little bit closer to Master's theorem and see that one is the merging is constant time, right?
Yes.
And dividing is not constant time.
Right.
If you see how it is going, it's kind of n to the power half plus 1/4 plus something, and it will somehow come closer to n or a little bit less than n.
So you're guessing the answer will be close to n?
So it will be dominated by the first breaking step, and it will be a little bit smaller than n.
Okay. Your prediction has been noted. So the idea that you should expand this out is correct. Okay? At this point, does anyone have an actual expanded out answer, or would you like me to just work through this now?
Work through it.
Shall I work through it? Okay. All right. Let's expand it. So this will be school. Now be very careful you do this. I'm going to rewrite this because it will be more convenient. Okay? I didn't do anything yet. Again, I haven't done anything yet. Okay. What does this become? Now be careful. You take the square root of whatever is inside, and then that same thing shows up inside here. And then you put a 1. Is that right?
Yes.
Yes. Where? Here? No. Which is equal to n to the 3/4 t n to the 1/4 plus n to the half plus 1. Oh, this is not as nice as I hoped it would be. Well, no, it's not. Sorry?
You can actually kick out the n to the power half outside. That is one kind of recursive which will be always coming out, right?
Wait, what? I just did it.
Okay.
Alright, let's do it again.
1/8.
I'm going to do it straight again. So this will be again the square root of this guy. So n to the 8th t n 1/8 plus 1 plus n to the half plus 1. What you're going to get here is you're going to get n to the 7/8. Hopefully you're seeing the pattern forming here. Plus n to the 3/4 plus n to the half plus 1. Is that correct? Right? Okay. Can we make a prediction as to what this looks like if you go through k steps? So just to help you, I'll rewrite this. Let's see.
Start approaching n factorial.
Wait. John?
Your exponents are tiny.
My exponents are tiny. Yes. In fact, they are. Exponent should be big. So I'm just pattern matching at this point. What you really should be doing, if you were a careful algorithms person, which I'm not, you would actually check by induction that if this is the claimed form, then when you apply one more step to it, you again get the same form. Right? So you can imagine, let's say this is true for k, plug it into the recurrence and see if you get the same exact expression for next one. For now, I'm going to just say by fiat it is, but that's because I know here. So first of all, before I try to parse this nonsense, when will it stop? When will all this stop? When will this stop? This will stop when this becomes a constant, right? Or 1 or 2 or something. When does that happen? Hey, if you're going to talk, put your hand up. I get confused. Yes. No, this thing did not happen. Okay. So, yes. With the cap, yeah. You were hand up? You did? Okay, sorry. I didn't mean to. Yes.
So after k steps, when 2 power
She was.
k, so after k steps, when 2 power k is so large that 1 by 2 power k will be 0.
Very good. You want to get to the point? Well, zero.
Sorry, 1. Yeah.
Well, more precisely, what you want is something like, and I'm going a little digression here. I want us to know when this happens. Sorry, John is going to scold me again. And rightly so. Is some kind of constant. I'm going to make it 2. You'll see why I need to make it 2. Because at that point we are at a base case, right? Because if this keeps going down, at some point we stop. When will this happen? K is equal to log n base 2. In fact, that is not true. Never answer a question again. Careful, careful. Take logs on both sides. What do you get? You get 1 over 2 to the k. Log n should be 1. 2 to the k should be log n. K is actually log n. It's very woody. So k is roughly log n. Okay? That's when this will stop. And that's when that will stop. So now what? So now the general form of this expression is going to be something like, in the limit it's going to be n to the 1 minus 1 over 2 to the k, where k is the last time this does this, times t of essentially 2 plus a whole summation of things. This is how I think about this. This plus a whole summation of stuff. Now, because by definition, let's see now. So you have to be a bit careful here. 2 to the k is going to be log. It's going to be log n. So it's going to be n to the 1 minus 1 over log n. So this is going to be roughly n. If you work this out, because the secret trick that you should remember is n to the 1 over log n is basically a constant. So this is n to the 1 minus 1 over log n. It's basically a constant times n. So it's going to be some constant times n. Okay. And this whole summation is going to be dominated by the top term. Right? So you're adding a 1, then you're adding a square root n, then you're adding an n to the 3/4. When you add geometric series, this is an important intuition to have, or series that grow even faster, the last term is the only one that matters. And again, this is not rigorous, but you can show that if you basically sum up, you're basically summing up expressions of this form, right? The last term is the only one that's going to matter here. And that's going to be basically n. So you're going to get something like an n from this term here. And this whole thing becomes n. So this is more or less what it is. You don't look so attractive, but you were correct. It's good. In fact, I thought the answer was different, and I was like, no, that can't be right what he's saying. And like, actually, you were right. So. Yes?
Can we not do it just the infinite GP sum?
You can approximate it by an infinite GP sum, but it is not infinite.
Yeah,
This is a discrete sum.
Because in case of saying that this n power 1 by 2 power k goes to 2, we can consider it to be 1 with 2 power k tending to infinity. So
Yeah, but then you have to sum up that to infinity. You can do all of that, but it will be an approximation. You will say that this is upper bounded by this infinite sum, and that's okay, because I want to get upper bound. That's okay. You can do it, but it's not exactly that. I'm doing the same thing here when I make this approximation. So yes, the short answer is you can do it, but that doesn't always work. Sometimes you have to sort of make these internal approximations. Okay. So in other words, sometimes the master will not apply, and you have to actually expand the whole thing out. A slightly simpler version of this, which I will quickly show you, is here, and you don't. I just want to look at it for maybe 1 minute. This is very easy to expand out. It might even be recognizable once you expand it out. This actually, as a record set, shows up quite often. Sorry? It's a harmonic series. It has a nice sweet sound to it. And then the answer is? See, that's the problem. But it's good that you know that, because that means you can go Google what is the conversion of a harmonic series and get the answer, which is fine for me. So, it's always good to recognize something. If you don't know it, you will not be able to show the closed form for this expression, by the way. This is one thing you just have to know. But let me quickly assert that if you just expand this out, what are you going to get? Don't worry about what in closed form. What is the summation going to look like?
1 by n plus 1 by n minus 1 plus 1 by n minus 2 plus 1 by n minus 2.
Right? Because this is going to be t of n minus 2 plus 1 over n minus 1 plus 1 over n. And again, going back to your constant, this will be basically summation I is equal to 1 to n, 1 over I. Now again, if you don't know how to sum this up, it will be very hard to figure this out. It's actually a very interesting, if you're taking any class in real analysis or calculus, this is a very important summation. Because each of the terms decrease as you go to infinity, but the sum doesn't decrease, it actually grows. Right? This is equal to, this is theta log n. And if you don't believe me, squint at this and pretend you're not summing it up, you're integrating it. And then you're integrating dx over x. And you all know what that is. Okay?
Yeah.
And yes, I should be saying ln n and not log n, but we're computer scientists. I don't believe in natural laws. But this is, by the way, another good trick. If you have some kind of summation and you don't know what it looks like, pretend to integrate it instead and get the answer and then just say declare that to be the answer. That often most of the time will work. Because it is rigorous, but you have to, there's a lot of layer you have to do to begin with. But it basically works. Okay. 2 examples where the Moss theorem does not apply and yet you have interesting records that you would like to solve. What I argued early on was that, last time, was that we think about recurrences and we obsess over these pointless recurrences because they give us patterns. Some of the recurrence tells us what the algorithm ought to look like, especially with divide and conquer. If you want to get an algorithm that runs in so much time, you kind of know, okay, it has to look like this. And that helps you go search for the algorithm, which is what you really want to do. We don't really care about the Moss theorem records, we care about the algorithm. But the recurrences help us do that. For example, hopefully at this point, if I say that I have this problem and I need to solve it in n log n time, and I need to use divide and conquer, what would you tell me to do? Okay, how about the middle section here behind the camera? Anyone? If I have a problem that I want to solve in n log n time and I want to use divide and conquer, what kind of strategy do you think I should be using? Anyone from the middle? Any thoughts? Yes?
My name is Anirudh. Make sure both the dividing step and the merging step are in the same.
That's good. You want to balance it because you know that there's some kind of log factor that'll show up. But I want n log n. I don't just want something times log n. Then I need to do a bit more. Can you tell me something more am I doing?
Plus merging.
Wait. Are you in the middle section? Anyone? Yes.
You have to make
Your
sure
name?
that, yeah, Chitrudi.
Sorry?
Chitrudi.
Okay.
You have to make sure that, during that merging step, you are not putting more effort than n times.
Okay, good. So first observation, we want them to take roughly the same amount of work because we'll meet case 3. Second observation, we want the merge to be roughly linear time because that seems to be the thing we want. Very good. One more piece of the puzzle in this middle section. One more piece we need. We know that the divide should be roughly like the merge. We know that merge should be linear. That immediately tells us what the divide should be. Trudy?
We don't want duplicate work.
We don't want to duplicate work. So what does that mean?
We want this to only look at each of the things in the divide step once.
Once. So you want to kind of divide them into pieces and never overlap pieces. Right. Is that enough? That's the like half of the final piece of the puzzle. So what you've all told me so far would give me a recurrence that looks like this. Let's say divide into 2 pieces. So I'm not doing any extra work because I'm not duplicating. Wait, and I do this amount of work for merging. Will this give me what I want? Okay, how about I don't know that half of that section there? Anyone? Will this you can choose the value. Will this always give me n log n regardless of the value of k? What do you all think? So there's a clue there. Regardless of the value of k. So plug in the actual value of k, whatever you want it to be. Let's see what happens. So for example, suppose I put k equal to 1. Okay, so we try and see. So we get t of 1 plus t of n minus 1 plus theta n. Now t of 1 is going to be a constant usually because it's a base case. So this is going to be, we'll just ignore this. This will be some constant. Plus t of n minus 1 plus theta n. What's this doesn't, the mass theorem does not apply here, but maybe you can tell me what the answer is going to be for this reference by expanding it out. So you're going to get you're going to get n plus n minus 1 plus n minus 2, and what's that going to give you? It's going to be n squared. So while we're almost there, there's some strategy in our design philosophy that needs to be fixed. What do we need to do? Divide by 2. Why? Because now if you think of the way that the computation tree is going, if you have a skew, it's just like, I'm la la la, and it's just going. But if they both are equal, they're both working at the same time. This picture is very important, this kind of balanced picture. This is the essence of successful divide and conquer, making things balanced, or roughly balanced. That means here we have to put k equal to n over 2, or something like that. So let's erase this. Let's make it n over 2 here, n minus n over 2 here, which we can simplify as 2t n over 2 plus theta n. And hopefully you all can now apply the masters here immediately and say, oh, this is going to be n log n. Did it matter that we had two pieces?
No.
So,
Yeah, you just need the same number
Your
of
name?
pieces. Chris?
You just need them to be equal.
Same number of pieces and same number.
And that's the same intuition. You want them all to be kind of working together. You don't want too much skew. Right? So for example, I could have written this as 4t n over 4. Using again through these factors, you don't want to do extra work. If you want to touch everything exactly once, so you have to do it this way. And then you make sure we have linear merge costs, as you said. And then we get this. Right? And it'll still be n log n. Again, you're going to check it up there and see. Yes?
But the equating factor is coming because of the big of n, right? If it's not big of n, the merging step is different from big of n.
Yes. It will not work. You're right. It won't work. That's why I said I want n log n. So just by looking at the master theorem, I now have a plan. I need to do something to divide things equally. I need to not do too much work on each. I need to make sure the parts don't contaminate each other. I do some work here, some work there. I need to find a linear merge step. Now you have an algorithm planned. This is much better than saying, oh my god, I have this big black box. I need to come over and log in algorithm. I have no idea how to do it. Now it's a plan. It says, okay, find a way to divide them so that when I merge, I take linear time. And find a way to divide them equally. Maybe you could just doubly divide them equally. Maybe you have to do some work to divide them equally. I don't know. But at least you have a better plan. And that's what I mean by saying that the thinking about the recurrence guides you to the algorithm design, especially for dividing. Okay? But suppose I want linear. Can I work harder at this? Constants are not going to help me. Can I be a bit more clever? So for example, suppose I divide things into more groups, but not constant. Something like this. Let's look at this reference now. I want to divide things into log n groups because log n is bigger than the constant, and why not? What is the solution to this reference? Again, you cannot apply the Mass theorem, but you can expand it. And again, we're not trying to actually solve it precisely. We just want to get something. Would this help us? We designed this algorithm. We want to get linear time. Could this help? Well, let's expand it. So you get log n times log of n over log n t of what? N over log n time divided by log of n over log n. Yes, it's getting to be an unholy mess, but that's why you don't actually want to solve it. You just want to get a sense of what's going on. Plus n over log n plus n. Okay? Now if we collapse all the parentheses here, remember that log of something divided by something is something, log of something minus something. So this is basically log squared n minus log minus log n log n. Okay? Times this monstrosity here that I will just call the monstrosity. This is how I'm actually serious. There's sometimes you just have to stuff. You know. Plus log n, that cancels. So that's just plus n plus n. Okay? This is not helping. Okay, let's simplify this. This is this minus that. So this number is less than or equal to log squared n times the monstrosity. But now you actually look at it. This is log n minus log n. There's a log n down there. So we're going to pretend, just for now. And again, this is hand wavy, but that's okay. We're just trying to get a sense of this. N over log squared n plus n plus n. I just did this because now you can see a pattern form. This is not rigorous. Don't ever confuse this for an actual proof, because I'm making all these simplifications. But it's an approximation that is mostly correct. Just to get a sense of this. Now you know what to do, because you did this with square root n. We need to figure out when this is going to stop. Okay? In other words, you need to figure out what power of log n is n, which is very strange. And again, a cool trick here is that basically, okay, we want to know what log n of the k is equal to n. You can't actually solve for k, it's going to be very hard, but you can guess. What do you think is a good guess for this?
E.
Guess, make a guess, it's okay.
E.
Sorry?
U is constant.
Okay, a constant. Let's put any constant there. Will this be correct? Well, let's take logs on both sides. This would be c times log n, and this would be log n. There's no way you're going to get this to work. C is too small. C needs to be bigger. But in fact, this tells you exactly what C needs to be. C needs to be log n over log n. So log n to the log n over log n. I am not succeeding in my mission if you don't hear logs in your sleep when you're sleeping. Is n. Which means this will run for that many steps before it stops. And you're adding n at each of those steps. Because that's not going to change, that's going to keep showing up. So you're running for log n over log n steps. And at each step you're adding n. So again, in our hand-movie world, we're just trying to get a sense of this algorithm. It's going to look something like the running time is n log n divided by log n. So we made the improvement. We got a bit faster, but not that much. Okay, maybe this is not good enough. We need to work even harder. We made some progress. So let's work harder. Can we use something like square root n? T of n is equal to square root n t of square root n plus n. Break them into even many more groups. You can work this out. You know, in fact, now you know already how to solve this. You know how many steps it's going to take to stop. We just did that. Log n steps, right? It's going to give you the same n adding up each time if you work it out. So this is going to be n log n. This is even better. But it's still not linear. In fact, today morning I was trying to prove that no matter what function you put there, you can't get linear. I failed. I'm very sorry. But my conjecture is that no matter what function you put here, as long as it's sublinear, you will not be able to get linear. So we cannot get our linear time algorithm by looking at sort of a divide and conquer approach in this manner. So what do we do? I don't care about recurrences. I want an algorithm that runs a linear time. How am I going to get it? And the trick is to realize that there is a recurrence that gives you linear time. We've seen it already. Consider the following recurrence. T of n is equal to T of n over 2 plus n. This is a very strange recurrence. You divide by half, you do a linear amount of work. But if you expand this, what happens? You get n plus n over 2 plus n over 4. It's a geometrically decreasing series. This is going to be n. Algebraically it's trivial, but conceptually it's very interesting. Because what it's saying is that if I want to get a linear time algorithm for a problem, it's not enough to divide things and then merge them. I have to throw something away. This is called decimation. So I don't know, how many of you know the roots of the term decimation? Not the signal crossing. You know the roots of the term from Roman times? So the ancient Romans, in their infinite wisdom, thought, we need to quell all these mutinous soldiers in our ranks. They go for a battle, they run away, they sit there, drink their tea, they don't do anything. This is ridiculous. So their technique for solving this problem was to have a lottery, which is basically a 1 in 10 chance of winning. And the soldiers that won were essentially disemboweled by their comrades. It was a rather gruesome way of solving their problems of decimation. That's why the word in common English is not a fun word. When you massacre an entire group of people, it's a decimation. But that's, for better or worse, where this idea comes from. That you take a constant fraction of your input and you throw it away. You do some work. You can do a lot of work to figure out what you need to throw away. But you throw it away. You never look at it again. If we think of our tree of computation, we had this tree where we had a bunch of nodes. We split them into 2 parts. And we split them into 2 parts again, each one. That was our n log n sort of familiar way of looking at things. What this is saying is that you cut off one entire side. Then you cut off one entire side. And so on and so forth. I mean, in this tree, it's clear what's going to happen. This will stop. The weird thing about this is it does take log n steps to stop. The log n is there. But at every step, you're doing less work. And this geometrically telescopes off. Yes?
So is binary search a good example of decimation?
It's a very good example. Binary search is also a very good example of decimation. It's a recurrence that looks like this. As a decimation exactly for that, because you have your point, you say, okay, am I in the left half or the right half? The left half or the right half? Depending on which half you're in, you throw the other half away. You never look at it. It's gone. And that's the key. There you get log n because you're doing very little work to figure this out. You do one comparison against the middle and you're done. In general, you might do more work. But what I personally find very counterintuitive is that it takes me log n steps of recursion to stop this problem. I have to do n amount of work at each step. So it should be n log n, but it's not. Because I'm dividing by 2 at every step. And of course, when I say divide by 2, I don't mean divide by 2. I mean divide by anything, any constant. Because the same argument would work. I could throw away 0.1% of the input at every step. This would still work. As long as it's a constant fraction. Because of mathematics, the geometric series looks like. Okay? So again, just to reiterate, till you're bored of my saying this, the recurrence guides the design. That's why we study. The recurrences guide the design. Come up with a way to throw away stuff, you will win. Your algorithm will get faster. You're allowed to spend quite a bit of time trying to figure it out. Yes?
So the most efficient decimation style of algorithm can be is log n, because that's how many steps it takes to finish.
I'm not sure.
Maybe.
Maybe. Okay. Maybe there's something. Whenever I'm asking, is this the most efficient, I'm always very scared to say yes. Because then tomorrow someone will write a paper and prove me wrong. Because otherwise I don't have a proof that you're correct. I can't think of anything on top of my head, but there might be something.
It's the same question. What if like we are decimating not a constant, like something like root of n?
Even more. Okay, you can do that. So binary search gave you, and that's a very good aspect. Because binary search gave you t of n over 2. Because suppose your recurrence in fact was t of n is equal to t of square root n plus 1. And I bet you at this point all you know what the answer to this is going to be. Because you know what happens when you take square root n over and over again. What do you think the answer to this recurrence is going to be?
Log.
Just like the binary search is log n, because you divide by 2, here you remove all the square root of fraction, it's going to be log n. In fact, there's a, how many of you have heard of a data structure called the Van M. Du Bois tree? Anyone?
What tree?
Van M. Du Bois is a Dutch mathematician. No, not you. So there's a data structure called the Van M. Du Bois tree, which works over integer domains, which is more powerful than a red black tree or a list search tree, which has a recurrence for querying that looks like this. In fact, it gives you log n time to do a query. It works because of the way you build it, because of you're working with integers and not over an arbitrary domain. So just like radix sorts gives you linear time, that gives you log n, and that has this recurrence. So yes, so you can do better. with decimation. That's why I didn't say it. Okay. I was going to cover what I want to do next, and I think I'll go to the next lecture, is to cover one of the most famous examples of decimation, that of median point. So you all know that the median of a set is a point, is the number that has half above, half below. And you can always solve this problem by sorting. You sort the entire input, take the middle element, and log n time your grade. But now you're saying, no, I want something faster. Can I do something faster? And so median finding is a perfect example of how you can use decimation to get a linear time out. And again, it's in the notes that I will put up over the weekend, and you can take a look at it. So we'll talk about it on Tuesday. All right.